Hello, so this is kind of another long form video that I'm doing. I haven't done a ton of those, I've done a few. This one is going over the code I have for Stable Diffusion 3. I initially did a session where I kind of coded the architecture from scratch. This is not going to be me actually coding it from scratch, it's going to be me going over the code I wrote that did it from scratch. Not the code I did before, some of it, but a lot of it has changed. It's very different because the last one didn't have dual stream and stuff like that. So this is going to be a lot of code that I'm going to be going over. And the reason I'm just going over it instead of coding it from scratch is because there is a lot of code. And the hard part isn't actually the architecture. That's kind of hard. The difficult part is everything around it as well that you add to it. So it's getting the architecture working as well as like the data pipeline and the and stuff like that, which I will talk about a little bit later. But I kind of also wanted to get this code available to have people so people can kind of train their own Stable Diffusion model. This I wanted to do this with 8 GPUs, and I have the code available here. I will put the link in the description if you want to try it out. So if you have 8 GPUs, you can train it from scratch. You can also do inference, but I think it's interesting to have some code that actually trains a model from scratch. There isn't a ton out there. There's a lot of stuff to fine tune a model, but there isn't a ton to train it from scratch. And I kind of made it verbose, or I tried to make it more verbose than a complicated, super efficient pipeline. But yeah, if you want to play with it, it's here. But I mainly wanted to do it for educational purposes, just kind of walk through it, and that's what I'm going to be doing here. The outputs are fine. I trained it to 512 resolution, so I have a 256. I initially trained it on 256 by 256 images, uh, and smaller, and then I fine tune it on up to 512 resolution. So these are some outputs for 512. I actually have 1024 as well, and the checkpoints are available if you want to try to play with them. But yeah, I'm going to be going over a bunch of different, or all the code here, or a lot of the useful code. But I mean, the outputs they're fine. They're good, in my opinion, for 8 GPUs, um, and not really optimizing the code that much. But I think it gets the point across for what the code does and how you would set up a pipeline like this. So if you're curious, there's a bunch of code, and I'm going to be going through that right now. So the first thing is the data. Actually, I'm going to go to the paper real quick and just show the data. So let's see, where is it at? If I go search and I go search data. Okay, that's just not helpful. I need to find it. So the main data they use is CC12M and ImageNet, if I can find where they say that. I think it's somewhere over here. No. Let me try this again. Search ImageNet. Okay, also not here. Yeah, oh yeah, here we go. So they do use ImageNet CC12M. So those are the two data sets they use. They combined them in some way. I think if you look down in the appendices, it doesn't say much about it. It just says that they use ImageNet and CC12M. So I have that available. I basically downloaded all of ImageNet and CC12M and kind of put it together into one data set and recaptioned all of it here. So there's the images, and there are the original captions, and there are the recaptions. So the first thing we need is we need data, and the data makes the model. So how good your data is how good your model is. And if you just take the ImageNet data and the CC12M data, you are not going to get a very good model. And I don't think that's what they do. They claim in the paper that they just take the ImageNet data and they take the CC12M dataset and they just train off that, but the images they have, there's no way that's what they do. If that's what they did, then they wouldn't get the outputs that you see in the actual paper, and it would be a terrible model. They claim that so if you know ImageNet and you know CC12M, I mean, you probably know ImageNet, CC12M maybe not, but ImageNet comes with classes. So if we look here, this is an ImageNet. I think this is ImageNet. Maybe not. Let me just go to the ImageNet one. So if we go to ImageNet, you'll see it is just data. Oh, I guess that was. It's just the image data and the class. And there isn't a caption. So they claim that the way they caption this data is by saying a picture of class name. So for this data set, was it 21,000 classes? That is a terrible caption. That is useless. And for CC12M, it is internet data. So if we go to CC12M, I actually don't think I have that by itself. It's probably going to be at the end. No. Here we go. It's loading. This is, I guess, not there. But it's basically just a bunch of internet data. So if you take the normal, just the alt text for some internet data, you'll get some CC12M dataset, or at least some of it, and that is not that good. You may have, like, if you know the alt text out on the internet, you know it's terrible. It can be informative, but it can also be terrible. So what I've done is recaptioned all of it, and it is shown that if you recaption your data, it is usually a lot better. So that's what this data set is here. It is both this is the ImageNet data set. This one here. It is both the CC12M and ImageNet dataset combined together with these caption datasets, as well as the height, width, and other stuff like that, because that is going to be needed later. So yeah, here we go. So I mean, this caption is pretty good. Like I don't know why it's not popping up, but it's pretty good. It describes the image pretty well, and it's pretty detailed. So I'll go through that right now. Basically, first part, I'm going to be going through the dataset, and then I'm going to be going through the code for the actual model after that, because the data is annoying, but it's necessary. So let me just go to the code. So this is just my Git pool of the entire code repo, and there's a bunch of crap in here, but under data there are two useful scripts. There's a lot of scripts there that I just have there, but they're pretty much two useful scripts that make this entire data pipeline. I also played around with Lion, so if you want to try to download that, I have scripts to do that. It is, I think, the biggest data set you could possibly find. Just know that you will need a ton of storage space. I don't even know how much that is. The dataset I have, CC12M and ImageNet, that requires, I think, 5 terabytes. The Lion dataset requires, I don't, hundreds of terabytes. It's an insane amount. So if you want to play with that here, go ahead. The reason I didn't use that is because I do not have 1,000 terabytes of space. I have 5, or I have more than 5, but not that much. So that's there. And it downloads everything to a folder. So if you want to try that, it's there if you need more data. Um, the problem is you would probably want to filter the ImageNet and CC12M dataset a little bit more. That'll probably give you a better model, but the Lion dataset, I have scripts for that as well. So the first thing is to combine these two datasets and then recaption them. So I have that under this. Where's filter? Oh, I can't see. So I have that under this, and there was I forget exactly what it's called. I think I mentioned it in here, how it was recaptioned. I think it was, if I go here, I kind of took how they captioned things and did it and reproduce that. So shout out to them for for describing how they did that. Um, they have down here. Oh wait, no, that's not the one. It's this one, Caption Emporium. Uh, Whoever this is, awesome, fantastic. Thank you for describing exactly how you caption everything, because I just took that and I captioned everything using that. They don't have a script for it, but they basically mention everything here. Oh, I didn't change the tab. If I go to Firefox, yeah. So shout out to them for doing that. They're the ones who did all the captioning, and they're the ones who had a bunch of captions out there for various data sets, and I just took their pipeline, not how they described it, and tried to reproduce it. So yeah, not my pipeline, or it is my pipeline, just how they describe, but it's just reproducing how they described it. So I didn't come up with the ideas that are here. So this is the pipeline here. It basically iterates over all the Parquet files. So it's just a bunch of Parquet files for ImageNet and CC12M, and it does a bunch of recaptioning. So I mean, not super exciting, but it has to be done. Um, so yeah, this basically it takes this and it converts it to high quality. I think that's this one. Oh, this one right here. Yeah, so this is it. There's a lot of stuff going on here. Basically, what we're going to do is we're going to take the image, we're going to take the alt text that comes with the image. So whether if that's ImageNet, it's just going to be a caption or an image of class name. And if it's CC12M, then we're going to actually take the alt text and throw it in there. And the idea is you take the model, or you take the image, you take the caption to kind of give the model a hint if it's useful, and it'll produce meaningful text. Like for example, the alt text can be useful if maybe it just says, like, I don't know, maybe there's an ambiguous animal or something like that. Like maybe there's some weird species of bird, and if me or you just looked at it, or if a model just looked at it because it's trained off data that is just out on the internet, it'll probably see it and say, I don't know, that's a bird or something. But if you maybe the alt text says what species of bird that is, so maybe that's useful. So kind of to make it less ambiguous, and it has been shown that if you give it the alt text, it usually does better for captions. There was a Facebook paper that I forget, I think it's called Alt Together, maybe that's it. They unfortunately didn't release their model, but it basically does this. And if that does come out, that would be really useful to recaption everything. But here I'm going to be using Lava and then Llama to make the captions a little bit smaller. So this is doing that. Basically, it just loads in every part of the parquet and it does these two steps. So I'll just go through that. So yeah, it's just processing all these parquets. I think I did it on one GPU. But so here, this is start recaption parquet. So it takes the parquet file and it's just going to add a caption column and a short caption column. So it's just iterating over that. And what it does is it gets the caption from Lava, from this Lava model, and then it gives it to Llama to make it a little bit shorter. And then I'm just throwing that in the data set. So pretty simple. So here is that. You have the image and the captions. So the captions are the alt text, and they're going to be thrown together in this Lava Llama 3 model here, and that'll produce something. And whatever that something is, so this is just a bunch of setup, just boilerplate code that's needed to run it through Lava. And I just send it through Lava, give it the image and the text, concatenate those together, and it produces the caption. And the captions are pretty good. I also do some processing. For example, if there's a lot of repeats in the caption itself, then I just throw it away. Or if there's like if it's way too short, then I also just throw it away. And there's some post processing. For example, the Lava model likes to add a lot of this here, a lot of these things. Again, this wasn't found by me. This was found by the caption Hugging Face I showed. So there's a lot of post processing here, and this is the prompt that they used for this. And it works. It works quite well. The captions it produces are pretty good. It's very hacky, but it gets the job done. It would be a lot nicer if I could use the alt together model, but it does work, and there are captions that are makes the captions pretty well. So that's that. Yeah, so basically just Lava and Llama to recaption your data. I mean, not super exciting, but again, something that has to be done. And if I go here to the dataset, go to datasets here, I mean, the captions are pretty good. So, and they're pretty descriptive as well. So that's nice. Now, once you have this dataset, there's a second thing that needs to be done. So if we look at Stable Diffusion 3, we know it is a patch-based model. So we know that the model operates on patches of your image. So that means if I have an image that is of size, like so for the model I'm using a VAE that downsamples by a factor of 8. So that means if I have a image of size 1024, I think it downsamples it to 128. I think that's right. So it downsamples it by a factor of 8. Then what I'm going to be doing is using a patch size of 2. If we look at what Stable Diffusion 3 does, it uses a patch size of 2 in the latent space. So that means that every token we have is going to be a 2 by 2. So I'll go ahead and draw this out. So let me go here. So we basically have an image here of size height by width. So this will go through our VAE encoder, and this will produce an image of size height by 8, W by 8. And then what we're going to do is we're going to patchify this into 2 by 2 patches. So this patch here is going to be of size 2 by 2, which will then be flattened to just a vector of size 4. Now what this represents is, since this here is 2 by 2 in the latent space, what this actually represents, this 2 by 2 patch represents a 2 by the downsample factor, so 16 by 16 patch. So that means that anything smaller than 16 by 16 is like, you basically want your image to be a factor of 16 so that you can tokenize it properly. If it's not a factor of 16, then you'll get weird things like, let's say you have to pad it in some way. So if you don't have an image of size 16 by 16, maybe say this token here will be of size, so this is 2 by 2, and maybe you're missing kind of that last part, then this part here will be missing, and that just doesn't work. You'll have to zero pad it, and it's just bad. So what I do is I transform all the images such that they are a factor of 16. And if you look at how it resizes things, it really isn't a big deal. If you have images that are of size, say 1024, and you resize it so that it is to the nearest 16, it's barely noticeable. And I just resize it to the nearest 16, so whether that's down or up, it looks pretty good. It's much better than adding these padding tokens and having to deal with padding. Padding is really annoying to deal with. So the first thing I do for this pre-processing stage is I take all the images and I have to resize them to a factor of 16. And that's because of this we're doing this 8 times downsample and then these 2 by 2 patches. If you were doing, say, 3 by 3 patches, then you would want to downsample by a factor of 8 by 3, or make sure all the images are of size 8 by 3, which is 24. So, yeah, that is the first thing. The second thing is you need to bucket your data. So what we're going to be doing is we're going to be taking from, like, we have our image data set. And what this will do is it'll, like, if I just randomly sample this will give me an image of size, I don't know, 128 by 256, and let me sample it again for another image. This will be of size maybe 64 by 128, 1024. So this is a problem. And the reason this is a problem is because we need to somehow combine these together into one tensor. And the way you do that is you can pad these two. So you take this one and maybe you add some padding here. Oh, this is of size 256. I'm going to pad it here such that this is 1024. So it matches this size here. Oh, this one is larger here. I'm going to take this and I'm going to pad it to 128 here. It's 120, 128 here. And then I can concatenate them together. Now, there are a lot of annoying things about this. One is if you try to deal with this padding in the VE, you'll run into problems. And that is because you have a group norm. You have a group norm in the VE. And if you have a group norm in the VE, it basically it normalizes in a really annoying way, and I guess just trust me that if you try to add this padding here, it gets really annoying. In the VE, if you have in the VE, if you didn't have any group norms, it would still be really annoying. Basically, if you have a convolution, like let's say our convolution is here, during inference, you won't have this padding. So what you want is you want to either make it such that the convolution doesn't look at padding, or an easier way, which is less efficient, is to basically mask your padded image. So what you do is you keep your original image and you make these 0. And the convolution is going to do 0. So if these are zeros here, the output of your convolution is going to be as if it didn't have this 0 output for, say, this pixel here. So for example, for this pixel, if I had like a 3x3 convolution, it'll take information from the padding, but since the information from the padding are all zeros, it would be like it didn't happen. Now, the problem is after the convolution, say this pixel here, also it takes information from the original image. And the problem with that is the output of the convolution will no longer have zeros in your padding. So that means before every convolution operation, you'll have to zero pad, you have to mask your image by zeros, or you can make something that is actually good on hardware. Now, if you just had that, it would be fine. Like, sure, it's annoying, but you can deal with it by just masking beforehand. Now, if we had layer norm, this would be fine. It would be fine. But the problem is we have group norm, and group norm does annoying normalization, which will take the padding tokens into account, and it becomes very problematic, and the way you would have to deal with it is just not worth it. And that's just the VE. So you if you deal with the masking in the VE, then in the transformer that we're going to use, the diffusion model, you also have to deal with masking. So just, it is not worth it. And what you can do instead is bucket your data. This is what you usually see. Now the way I am going to bucket the data is maybe not the most efficient way. It is a way, and it may not be the best way, but it is a way. Is if I have my data set here, that is a larger data set than that one, I guess. Whatever. So I have my data set here. We already know that I have, like I already mentioned that I make everything to the nearest 16. So what that means is all my images are going to be either 16 by 16 or 16 by 32 or 32 by 16 and so on. So they're all going to be factors of 16. And this is really nice because this means our data is already bucketed. And that means we have a bucket for every size that we have. So that's awesome. Now, at the beginning, I mentioned I train on size 256 and then size 512, and I fine tune on size 512. That means for a dataset of size 256, I can bucket all the data by labeling every image with their corresponding bucket. So for 256, the lowest resolution would be 16 by 16, and the highest would be 256 by 256. So however many there are here, there's not that many, you can bucket your data into that. And yeah, so that's nice. Now, to get the data in 256 by 256, I just downsample it and maintain the aspect ratio, so not a big deal. So basically, what I'm going to be doing is I'm going to downsample the data, or I'm going to take the data, I'm going to make sure they're all of size 16, or they're all near, or they're all closest to a factor of 16. So all the images are a factor of 16. Then I'm going to downsample all of them such that they are below 256 by 256 resolution. And then I am going to bucket the data after that. And this will be the data set that I'm going to use for the first stage of the training pipeline here. And then once the data is bucketed, I can say, let me just randomly sample from my buckets. So this will be a distribution here, and maybe, I don't know, 128 by 256. Maybe this is each of these will have a frequency, and maybe this is, so it'll look like some distribution, and you can sample from there, and maybe, so assuming the data set represents images you would want to produce, then whatever the highest frequency resolutions are going to hopefully be the resolutions the user wants to generate. So if I sample according to that distribution, I can hopefully get a representative model for that. For example, you're probably never going to produce an image that says 16 by 16, but maybe 256 by 256. Maybe that is a high frequency. Maybe in order to do that. So yeah, it's going to be sample a bucket, and then this will give me a easy batch of images, which I don't have to worry about padding because they're all the same size, and then I can throw that through the model. So that's the second part of the data set. Let me go to the code, which is pretty simple. I have that here. Basically, all it does is it just iterates through it, and it looks for the which one is higher with their height, and it just resizes the images here. So this just resizes and maintains aspect ratio, and then it creates the bucket size here, and it puts all that data, all that information in the data set. So if I go to my data set again, and I go to the data sets that I have, I haven't put the 1024 one up, but if I go, I have two data sets, 256 and 512. If I go to 256, we can see there are the aspect ratios and stuff, and there are the bucket sizes here. It looks like the largest bucket size is 256 by 176, and the second largest is 256 by 192. So yeah, these are the buckets that we use, and there will be a distribution that'll be sampled according to the bucket size, and that'll give us the corresponding bucket that we sample the images from, and send that batch of data through the model to up to do normal model stuff that you would do, so flow matching loss and stuff like that. So yeah, that was the data set. There's a lot of stuff for the data set. It's not, again, not that exciting, but it's there, and I wanted to talk through it because it's not as simple as just taking the data set and loading it, and that's it. You have to do a lot of pre-processing for this data set. But now for the interesting part, the actual model and the code. So let me go through that. So let me go back to this. Now, this is the model. This is everything that's going to be coded. I will go through the model step by step, starting from the this part of the model. No, that. Starting from this part of the model and then going to the details of the model. There are a few things that are wrong here. So I have made a video on Stable Diffusion 3. I'm going to assume you know Stable Diffusion 3 and how it is working. Mostly, it'll kind of be a refresher, but I'm not going to be describing this is why this is done in Stable Diffusion 3 in detail. But yeah, so hopefully you already know kind of the idea behind the architecture. It's a dual transformer. Basically, it's a transformer. It'll take in our noisy image and it'll produce the velocity output. But it also takes in a big tensor, this big massive tensor, which is a concatenation of T5 and two clip models, which is the dual stream. And what happens is you have this dual stream of text and images which can communicate with each other, and the output will be the denoised image. And then you also have this here, which is this pooled representation of your text, which will be used to kind of change the statistics of your data. And yeah, that is also there. So this is a flow model, as I mentioned. That means we're going to be modeling the loss. We're going to be modeling this as this here, so rectified flow. I didn't add anything else because rectified flow is just so easy to do. It's just, I have my original image x0, 1 minus t, I take a random time step, and I'm going to just do a linear interpolation between the image here and some random noise I sample. So it's very easy. There is going to be something I mentioned with the loss later. It's going to be it's going to be how you weigh this, but I'll talk about that later whenever I get to that. Mainly, I want to talk about the model first, and then I'll talk about the training that is done for the model. But yeah, so the model here. So the first, I'm mainly going to be talking about this part here, this big part here, and then, as I said, I'm going to go into detail. But yeah, hopefully you already kind of know the idea behind the Stable Diffusion 3 model. Two streams. One is a big tensor of data, and the other is this image part. I get with this vector here that controls the statistics of of the model at that time. So let's go over to the code. So enough of this data. I'm going to go to this model here. So diffusion model. So this diffusion model is going to take in this stuff here. Basically, it's going to take in the image at time step t. So this is going to be this is the forward pass for training. I have the inference down here, sample images. So this is specifically forward pass for training. It takes in a noisy image. It takes in the time step of said noisy image. It takes in C, which is going to be that big tensor that we are like the big tensor that's going to be in the second stream. So image will be in one stream, C will be in the other stream. And specifically in my case, this tensor is 154 by 4096. I think that's right. I think it is 4096, but basically it's static in both the time dimension and both static in the sequence dimension and the dimension dimension. And later I will talk about how this is done. I have a method for doing this while the model is training. There is a lot of annoying stuff that you have to do to get this to actually work. Uh, like it's non-trivial how you would get this to work, how you actually load in all the data. For text, it's easy. You load in the data and you tokenize it. But for images, it is not, because you have to tokenize the data. In my case, it's going to be in two ways. I use Gemma. So in Stable Diffusion 3, they use T5 and two clip models. I use Gemma and ModernBERT. So I have to tokenize the data twice, but I also have to send the image through the VAE. And that takes forever to do, and I'll get to how I got around that later. But let's just assume we have this tensor, which is again, in Stable Diffusion 3, it is a concatenation of T5 and clip, and in my case, it's going to be the concatenation of this Gemma tensor and this modern BERT tensor. So it's the same idea. If I go back to this, you can see this is basically the T5 output, and this is this here, and this is the clip outputs. And see, this is static here. This is 154, and this is also static here, the dimension part. So that is that. And then the third thing is this C pooled tensor, which is going to be this vector here. That is the pooled variant of the text input. So let me go to that. That's this part here. So C pooled. So basically image, time step, big tensor for text, and vector embedding for the text. And then there's these three parts here. In the original Stable Diffusion 3 paper, they used, I forget what value it was, like 0. Actually, I think I wrote it down. 0.644 or 0.464. And this is the probability of dropping one of these tensors out. So this is going to be a mask that drops out the tensors. And basically this allows you to do null embedding, but dropping one part out at a time allows you to see what's important. Maybe the Gemma model isn't that important, and if I drop it out, then the image outputs will be just as good as if I didn't have it there. So that's why you drop every piece out with some certain probability. Specifically, we want to drop it out with a probability of 0.1 because that works. And that was kind of what was done in the original paper, and it just works, and that's kind of been the go-to right now. So a probability of 10% to drop out things. So the pooled embedding itself is just dropped out with a probability of 10%. For me, the pooled embedding is coming from a clip model. So that has nothing to do with this Gemma or BERT model. It's just this clip model that I'm using, and it gives me a pooled embedding. So that's point one because there is no dependence on anything. Now this Gemma and BERT part, since you have this tensor that's a concatenation of those two, I am dropping out the Gemma, so we basically want to drop out the entire text, or the entire text input with a probability of 0.1. So if we drop it out with a probability of 0.1, then maybe we want to drop out the Gemma model and the BERT model with an even probability. So basically you want to find the square root of 0.1, and that's just this here, 0.316 about. And in the case of in the case of Stable Diffusion 3, they use three models. Again, it was two clips and a T5. So you find the third root, and that's 0.434. And if you multiply all those together, you get 0.1. So in the expectation, you get it gets dropped out with 10%. So here I'm using 3.16 or 0.316 because I only have two models. They use 0.464 because they have three. So these are just masks here saying it's a 1 in the batch if I drop this out, and it's a 0 otherwise. So that's all the inputs here. Now here is doing the actual dropout. So this is saying if like wherever this is taking C pooled, it's taking the mask in, and it just multiplies it by 0 if it's being dropped out, because it would just be 0 if you're dropping it out. That's just how I'm doing the null conditioning. You could do the null conditioning another way, but I'm just doing the null conditioning by multiplying by 0. And since Gemma and BERT are concatenated along the sequence dimension, you can just drop out the first part or the second part of the tensor. So if I go back to flow, basically it's just dropping out either this part or this part here. Now the weird thing here is they have clip and clip, and they concatenate along the dimension, and I find that weird because this assumes that, say, so this is one clip model and this is another clip model. That assumes the embedding, so this is some sequence. This is maybe it encodes uh, this is a image of a bird. So that assumes that this embedding here for clip L14 and this embedding here for G14 both represent the same idea because it's embedded on the same dimension. Now that doesn't make any sense because these models are different, so I don't like that. Like it makes a lot of sense to concatenate along the sequence dimension because that's saying here are more tokens describing the text, go ahead and do what you want with it. But if you concatenate along the dimension part, that basically says the information in the position is going to be like semantically the same. It's a different way to describe said information. That's kind of how I think about this here. So this embedding here represents maybe bird, however, however T5 wants to describe that or embeds it. This here will likely represent two different ideas, and they're concatenated along the dimension, so that doesn't make much sense. So that's another reason why I'm using only two models instead of three, because if I used a third model, it would basically expand it the sequence dimension out more. So anyways, back to the code. We just mask this to do the null embedding, and here, this is just making sure t is in the correct form. So this is just basically embedding t. So t is a time step between 0 and 1, and that is encoded here. So the first part, let me drop this over here. So if we look here, the idea is I don't know how the model kind of wants to scale the time step. So it's a value between 0 and 1, but I'm allowing the model to basically move this value around. For example, some other models used a value of like 1,000. So there's this very wide range that you have. And what we're going to do with these is we're going to take this time step and we're going to throw it through a positional encoding. So we're basically going to get these Fourier features that describe this model. Now, if I have a value between 0 and 1 and a value between 0 and 1,000, the Fourier feature range that you're going to get is very, very different. So I don't know what that range should be, so I just let the model pick it, and I initialized it to 1,000. So basically it's going to take a value between 0 and 1, convert that to a value between 0 and 1,000, and my hope was maybe the model will have maybe it'll find the range it likes best. So and maybe it'll make a 0 if it doesn't even want to use it. So it takes this, it scales it, and then it does this t embedding here. So this t embedding is just this positional encoding here. And this positional encoding is just what you would see in a normal transformer. It just does the Fourier features for a one-dimensional time step. So this is like if I took the ith token in my transformer and I just threw it in here. Basically, it takes the time step and it just rotates it based off that time step, and then it computes the sine and cosine of those. So this is just, if you look at the original attention is all you need paper, this is just doing that embedding. So that's that here. And again, it can scale that to whatever it wants. So it can find the range it wants to pick. And then t embedding 2, which is here, is just a linear projection to the dimension. So yeah, and this will be the first part of our encoding, our vector encoding. So that's this part here, just embedding the time step, letting it pick the range it wants for the time step. And this part here wasn't added, it was just something I added just to see what would happen. C pooled, so we have this pooled embedding, which for Stable Diffusion 3, this was concatenation of the clip models. For me, it is the output of one clip model. So this here, it takes the pooled vector embedding and it just projects it. So if I take that, throw that over here. Oop. Oh, not sticky keys. Okay, I don't know why it's not behaving. But if I go to, I'll try this once more. Oh, there we go. Yeah, so if I go to here, conditional MLP, it's literally just an MLP that takes the class dimension and projects it to the normal dimension. Oh, so the shape in Stable Diffusion 3 was 4096 because of T5. For me, it's actually 2304, it looks like. Yeah, I didn't use T5 because it was so massive. So here is the combination of the text and the pooled embedding. So that's just concatenate or adding the two together, and that is going to be the embedding that conditions all the statistics in the model. So that's that part. Now the second part. So we have this vector, which is just pretty simple. The second part here is this big class vector. So again, Stable Diffusion 3. This was the concatenation of this T5 embedding and these two clip embeddings. For me, this is going to be the concatenation of this Gemma embedding and a modern BERT embedding. So these are two different embeddings here. And what I did is I normalized them differently instead of normalizing them as the same thing. So you could take this output and you could normalize them using the same normalization. I did them independently, so the first 77 tokens comes from is going to be normalized different from the second because they should have different statistics. They do have different statistics. The output of Gemma is massive, the magnitude, and I think that's because it's a decoder transformer. And basically, the idea of like, of course, an encoder only transformer should be better than a decoder only transformer, but because the decoder transformer, they currently are being developed a lot more. There's a lot more good data going into a decoder transformer. The embeddings for them are pretty good, and that's why I'm using Gemma. It was also described in a paper by NVIDIA here, where they said this is the Sana paper. If we go to Gemma, they say why do we replace T5 with Gemma, and they mention here it's pretty good. So they use Gemma, and I just did the same thing. So if I go back to the code, basically I'm taking these two outputs, I'm normalizing them differently, and projecting them. Now, since the outputs of Gemma are so massive, I have this learned scalar here. Here, learnable scalar. And what this is initialized to is 0.01. I think the output of Gemma is in the order of magnitude of like 1,000 or something like that. And if you just natively embed this, it doesn't work. They also mentioned this in the Sana paper. So this is just scaling it down. It can learn this value here. So if it wants to scale it back up, it can. Hopefully it's stable. It seems to be stable. And this is just doing the projections here. So C1 projection and C2 projections are just linear projections. And then I also have these normalizations here. So basically, I'm taking the raw embedding for Gemma and modern BERT. I'm normalizing them. I'm multiplying this by some learnable scalar, and then I'm doing a linear projection. And yeah, that's just embedding this big tensor here. And finally, we do this here. So this is the positional encoding for the image itself. So one thing to note is there is no positional encoding added to the text embeddings, and that's because it may bias the model in some way. So it's added to the positional encoding is added to Gemma while it's doing the processing, and it's added to uh, Clip and T5 and Modern BERT as it's processing it. But I'm not adding it explicitly to those output embeddings because it doesn't need it. If it wants to pull information for the ith position, that doesn't really make any sense. Like if I'm generating an image, I don't care what position the information is. I just care that said information exists in the prompt. Mostly for the embedding part, like the embedding part, not for the text. So these are some output latent embeddings that represent the text in some way. So I just want to know that that information exists and it has some properties with the rest of the text. So I just pull that information. If I bias it with the time step, it may harm the model. So I don't add any time step embeddings here for the text, just for the image. Now for the image time step embeddings, well, there's two parts to it. This is the original. I think this is in Stable Diffusion 3. I think that's where I stole this from. But I don't use it how they used it. It's just two parts that I use it for. The first part is to patchify the image. So this is patchifying via a conv2d. So usually you would take every patch, every 2x2 patch, and that would be it. Here they use a convolution to take every 2x2 patch, but they use a conv2d to instead of doing normal patchification. So the kernel size is patch size by patch size, and the stride is patch size. So basically, this is a convolution over every patch to allow it to learn whatever it wants to learn instead of you biasing it and just unpatchifying everything. So yeah, hopefully that's better than just native patching. That's why I just left it there. And the second part is this 2D sinusoidal embedding. So I initially showed the 1D sinusoidal embedding, the idea with 2D sinusoidal embedding is I can take the first half dimension and I can embed that with the 1D or with say the information going along the one axis, and I can take the second part of the embedding and embed it with the second part. So let me go here. So if I have some image here, if I just do 1, 2, 3, 4, 5, 6, 7, 8, 9, that doesn't tell me, like my image could be this. I don't know if that's 9. 1, 2, 3, 4, 5, 6, 7, 8. Oh, it was 9. Nice. So these images are the same with respect to the image, with respect to these positional encodings I have. So this encoding scheme is dumb. It doesn't work. It is useless. So instead what you can do is you can take the 2D positional information. So we have the positional information 1, 1, 1, 2, 1, 3, and this would be 2, 1, 2, 2, and 2, 3. So this makes it's no longer ambiguous. Now the way you do that with rope is you say I have this embedding here, which you would normally do. You would normally throw for sinusoidal features at it for whatever position there is. So like a normal transformer, you would say this is position 5. Give me the embedding for position 5. Instead, what you do is you cut this in half and you say this embedding represents the first part, so it represents this part here, and you just throw that through and get the normal embedding saying this represents the axis 1, this represents a value 2 on axis 1, and it gives you that. And the second part here does the second part. So this represents the second part of axis 2, and so on. Like this is it's just breaking the embedding up into two parts and doing that. So pretty simple. It's just a different way of doing absolute embedding for 2 dimensions. So that gives you this. And that's basically the two things that this patch embedded does. There's other things it does. I played around with using Nope and some other versions of Rope 2D, and they weren't as good, but yeah, this is basically what it does. I actually don't add the positional information. So I mentioned that this adds positional information. I use rope instead. So rope is the same idea. Instead of adding this absolute positional information, since rope tends to be better, I actually use rope instead of adding these absolute positional embeddings to the very beginning of the image. It's an option in this code, but I don't actually do that. In attention, it's the same idea. You normally have a rope embedding that you add to a vector, but instead of adding one rope embedding, you add two rope embeddings that represent a rotation along one dimension, the height, and a rotation along the second dimension, the width. And it's the same idea. It's you cut up your embedding into two parts. So basically all this is doing is it's doing patchification, but it also does positional encoding if you want absolute positional encoding. This part here, let me remove this. This part here, patch embedding, is I think just a linear projection. Yeah, it's just a linear layer. So just more parameters, I guess. So it's just embedding it again. So then now that all this is set up, I throw this through a bunch of transformer blocks, which is what you see in the paper, where this is our image. This is the second big text tensor. This is the text and time step embedding, and the original shape, just so I can get the original shape output. This is so that I can get the right positional encoding information. Again, this is a flattened tensor here after it's patchified, which is ambiguous with respect to what the original image is. So the original shape tells me what are the 2D positional encodings I need. So it informs me of that. Then once we send it through a bunch of blocks, this is an out norm and an out projection, and then it's unpatchified, and it is done. So that is that. I also have this here, this text loss, which I was playing around with. The idea is if a model doesn't follow a prompt well, if what happens if we train the model to not just learn how to denoise an image, but to also do next word prediction. I didn't end up playing around with it a lot because I didn't have that much compute. I didn't have enough compute to play around with it. But yeah, that was there. The idea is maybe it would follow it more if it had to model the text itself, so that this second part would be actually useful. So let me go back here. So that is this part here, except here I use this right here is a clip model. I think it was MetaClip. This part here for me is Gemma, and this part here is ModernBERT. And there are a few extra things I added there, and I also don't have this, I have rope. So now for the MMDIT blocks. So everything else is there. I just need to go through the MMDIT blocks. So this is what they look like. Hopefully remember them, but basically it's just this dual stream attention where you have where the text and the images are being processed separately and they communicate via attention. So let's go over that. It's not that complicated. Again, the model isn't like the model's just very big. There isn't anything too complicated with it. So let me go over that. Transformer block dual. I was going to add a single block. So if you look at the, I think it's is it Flux? I think it's Flux. The go-to image model right now. They use a set of dual transformer blocks and then single layer transform or single stream transformer blocks, and basically you can reduce the computation by concatenating the text and the images and just going through a single stream after you've done so many dual streams. I think they do 1 to 2. So they do, say, 30 layers of dual stream, and then they do, say, 60 layers of single stream. And it's a lot more efficient to do single stream because you process things in parallel. If you concatenate the text and the image together, and you send that through a feed forward, that's much faster than sending them through individual feed forward layers. So yeah, let me just go through this one at a time. So why is the embedding for the vector embedding? One thing I want to note is they say they send this through Silu and then Relu. I think they have this flipped. Does it make any sense to take a vector and apply Silu every time? No, because you can apply Silu. Like, that doesn't make any sense because the vector isn't changing at all between your blocks. It does change if you apply a linear layer and then Silu. So that's what I do. I apply the linear layer and then I apply Silu rather than apply Silu. Like if you had Silu here, it could have just gone right here. You could have just had Silu right there. It's the same thing. But if you have a linear layer and then Silu, then it makes sense. So that's one thing to note. Another thing to note is they have this residual here, where this residual is applied here and here. Now if you do that, it sucks. The residual should be this one here, but then it should be this here, which is what you have in a normal transformer. But yeah, I think those are two things that they messed up on the diagram. Yeah, so this here does the linear layer and then Silu. This is just embedding the vector here. This here is applying Swidelu. Uh, I forget exactly what they use, and I think they use a GLU MLP. I use Swidelu because that's the go-to one right now. So I have this MLP, which is just Swidelu. I think, yeah, I use Xformers for this, but I also have the MLP implemented manually. So yeah, that is Swidelu. Swidelu and then normal attention, and then you have a bunch of layer norms. So I'll just go through this step by step. So the first thing is, or you have a bunch of norms, not layer norms, or I guess they are layer norms. So you have your projection here, and this is just projecting your input, or this is just projecting the vector here, and then applying Silu. Here is the attention layer, so I checkpoint attention, and you pretty much always want to checkpoint attention. If you don't, you are wasting a ton of memory, because if you don't checkpoint it, it has to store, like, your model is not is probably like it's not. It's really fast. It's really fast to compute attention. The problem isn't the speed. The problem is a lot of is usually the memory requirements for attention. It usually requires a lot of memory to do these things, especially with an image with like 1024 patches or of size 1024 or large images because there are a lot of patches. And if you don't checkpoint, it'll basically have to store the intermediate tensors for the entire computation, and that includes your QK transpose matrix. So checkpoint your attention, even if you're using flash attention, which basically does checkpoint it, you want to checkpoint attention because it is so fast to do the attention computation that there's no reason not to. So here it's just checkpointing it, it's applying attention, and it is, yeah, so let me go back to flow. I'm saying flow. That's the program I'm using to communicate my tablet and my computer because I have a Samsung tablet. So here we have layer norm, and we apply the statistics for our layer norm using the vector statistics here after this linear layer. Here I think they apply linear layers as well. So this layer norm, normalize your image and your text, and then you do attention here. So I'll just go through that part. So here, this is applying the norm to the image part and the text part. And if I go to this norm here, all this is doing is it is taking the input, it's applying a layer norm, and it's applying this conditioning here. So I do 1 plus scale to bias it towards a value of 1 initially. So a value of 1 means that it'll be multiplied by a value of 1, meaning it doesn't change the scale of the vector at all. And this is initial, and this doesn't have any bias to it. So that's that there. But basically, it's multiplying to scale the value, change the variance, and shift the mean over. So layer norm, good old zero mean, one variance. This changes the variance, and this changes the mean using that vector information that we have. So that is this here. And basically we're doing that for both the image and the text here. So then we apply attention, and the output of attention is just going here. So this gives us two outputs. I'll go through the attention code in a second. I mean, it's just normal attention code, kind of dual stream attention code. And this will give you X, which I then, so there's this second normalization that's done, and basically you have your residual here, but you have this this kind of glue operation here, where you take your vector here, and you allow it to change the statistic. You allow it to basically act as a gate for your output. So you have your attention output, and you have your vector here. You throw that through a linear layer, and this linear layer basically controls it's basically a gate on your output, and then you have your residual here, which is just the input into attention. So that's this here. The second part here is the MLP, which is the same idea, the same exact operations, except instead of doing the attention layer, it's just the MLP layer. So here we have the norms. So this is the norm for the text. This is the norm for the image, norm for the text. Again, controlled by this y vector. And this is the MLP. The MLP is applied to said normed variance. Then we have our y vector here, which acts as a gate on the output, and then the residual here for both of them. And this gives you an output. So if it's the last layer, I have to basically say don't compute this text output because it'll produce gradients, and then DDP will get mad at me because there are gradients it doesn't backprop through. So that's why this is here. So yeah, simple. Let me go to the MLP. So MLP is just SWIDLU. Again, I think they use GLU in the paper. So GLU is just this up projection, and then you apply GLU, and then you have the down projection. For SWIDLU, it's an up projection. I just yeah, I just converted to X formers. But basically, you have this up projection, which gives you your gate and your input. The gate goes through a silu layer here, and it gates the up projection, and then you have your down projection afterward. So I mean, it's literally an MLP. It's super simple. Now for attention, it's less simple because you have dual stream that you're dealing with. That is a lot of red. Whatever. It's it's Pylance being annoying. I need to turn that off. So you have your input X here, and you have your text here, and original shape here, which is going to be used for the rope embeddings. So I was going to implement this with single stream. I think I did implement it for single stream. I just never used it. I just used a bunch of dual streams because I didn't feel like playing around with single stream, but it's there for single stream. Basically, for dual stream, which is the path we're going to be following, you have your this projects X to your queries, keys, and values. So project the images to Q, K, and V, and then you reshape it to the number of heads here. So this is project to Q, reshape so we have however many heads we want. I forget how many I use. I think it's 16. And then transpose so that the head dimension is in the right dimension. So you basically have n, so you have b by n, b by n by d. And what this will go to is b by n by h by d sub h after you project this to the number of heads. And you want to flip these two, so that's what the permutation does. So this will go to b, where b is the batch dimension, by h by n by dh. And if you don't flip these two, then you would basically be doing attention where you have this attention matrix on the heads, which doesn't make any sense. So the permutation makes it where it's attention over the sequence, which is what you want. So the queries and the keys are also normalized using RMS norm. So that is this here, and that's what these are doing. So this here is just project Q from X, reshape it so that you get the heads, permute it so that the head is in the right place, so you're doing attention over the sequence, and then normalize. And this is the same for the keys, and then the values don't have any normalization. And you do the same thing for the text because we're doing dual stream, so it's just the same operations in the text. And this here is a single stream, but I'm not worrying about that. Yeah, same thing. So I played around with linear attention a little bit just to see what would happen. It was fine. It was just better if you use softmax attention and flash attention. So if you take, so once you have that, you want to apply rope. And like I said before, you have rope, you're applying rope 2D. So you can apply rope 1D. That's the same idea as if you have 1, 2, 3, 4, 5, 6, 7, 8, 9, which sucks. Instead, you want to apply a rope 2D, and basically this gives you a vector that you're going to add to each token, and that vector will be cut into two parts, where the first part represents this. Basically, it indexes the height, and the second part indexes the width, and it rotates the vectors accordingly for that. So queries X, keys X, it gets the frequencies, where the frequencies are these vectors that are cut into two. For the first, and like I mentioned before, it just rotates them. So same idea that for normal rope, it just rotates it in two ways instead of one. And this is another thing I was playing around with. Basically, the idea here that I was playing around with is instead of doing a normal rotation, why don't you do rotations where you have, like for 1D rotation, you just rotate it normally. But in three-dimensional space, you have three rotation matrices you can use. What if you use two of those here? It was about the same, but I wanted to play around with it anyway. I also played around with merging the keys and values. I didn't have enough time to play around with that either, but so far all we've done is we've created QKV for both for the text input and the image input, and then we rotated it for 2 dimensions using rope. So now if we're doing the dual stream, we have to concatenate the queries, we have to concatenate the image and the text together along the sequence dimension, so that is done here. And I just keep track of some information to make sure I know which parts are which. I use flash attention, so that's just flash attention here, normal flash attention. But if you didn't use flash attention, you would do inner product, scale, mask, values, normal, good old attention, where these queries and these keys are the concatenation of the text and the image, so it's literally normal attention. Again, I was playing around with some linear variants and seeing what happened with those. The dual stream then needs to break up the text and the image, so that's what happens here. It takes the attention output, it breaks up the two, and then it removes the heads for both parts of, for both the attention outputs for the text and the image, and then it does some output projections here. I need some coffee. Much better. Yeah, so then it does some out projections here. So yeah, that is the transformer block with the tension and the MLP. Pretty simple. It's just keeping track of information properly. But yeah, that's the model. The model again, not that complicated. And yeah, I mean, there you go. Now, what we need to do is we need to go over how do you train this thing. So let me go to the model trainer. I don't know what changed here. So we need to train this thing. Now let me go over that on the paper. So going over all this, we now have a model that does things, but it doesn't do the things we want it to do. So let's train this thing. Now we're going to train this thing using this loss function here. And what this loss function is it's just MSE between the output of the model and the noise itself, except we're going to be training a flow model. So we're going to be doing flow matching. I don't know if they have the loss over here for flow matching. Yeah, they do here. So for flow matching, we are matching the velocities of the model. That means our model is predicting a velocity, and we want to train it on the velocity. For said velocity, let me pull up what the value is. Actually, I think they have the value over here. I can't find it. Basically we want to train on. I have it here somewhere. Here we go. So if this is our loss here, this is going to be the velocity output. Our label here is going to be, so if v sub t is equal to alpha here, this is our v sub t. Then if we take the derivative of this, so the velocity, then this would just be, so v sub t is going to be equal to epsilon minus x. The way you get there is just by taking the derivative. So if we take the derivative of this with respect to t, then this would be negative x sub 0. So the derivative of this with respect to x plus epsilon. And that is equal to epsilon minus x0. There. Very, very easy. And this is going to be our label, just the velocity. So what this will do is this will point in the direction of the noise, I'm pretty sure. And you'll just reverse that to get the direction of the image. So that is u sub t here. That's going to be our label. Epsilon minus t. No, epsilon minus x0. There. Yeah, so that is that part. Now there's a second part to this, and I don't know. They have it here. I don't think they have it over here anywhere. But basically there's this weighing scheme. So if you look at, yeah, I think it's this loss over here. There's this weight, there's these weights here. And these weights basically focus more on, so notice how they're indexed by t. Basically, this puts more and less weight on certain time steps. So some time steps are more important than other time steps. Now, intuitively, there are some time steps that are, like, you can probably think of some time steps that are more important than others, and the intuition you have may be right. because time steps near t is equal to 0 and t is equal to 1 are very easy. So if we go to the velocity so the velocity is 1 minus t. Let me go back over here. So if we go to the velocity here, it is 1 minus tx0 and t epsilon. So if we have t is equal to 0, this would be x0. That's our input. Now it is very easy to predict the velocity for this. The velocity is 0. Like there's no velocity. You're at time step 0. And if you wanted to predict the image is x0. So that is very easy at time step 0. Now if you look at time step 1, it is also very easy. You have at time step 1, you have epsilon. And it's very easy to predict the noise. That is just epsilon. So at the tails, it's really, really easy. However, in the middle, at 0.5, it is very difficult. So they have this thing here. And this, I'll show you what that looks like if I go down here somewhere. There exists an image I am looking for. I will hopefully find it. Right here. So if we look at the time steps, at time step 0 and time step 1, you have a very low weight. Well, at time step 0.5, you have a really high weight. And the one they use is this orange one, mean of 0, standard deviation of 1, I think. And basically, this says this is weighing the time step. Now, an alternative approach, so this is fine. So what you usually do is you take a time step and you sample it uniformly. Now, what we're going to be doing is so you would take a time step, you would sample it uniformly, and then you would weigh the loss by this. So that would mean that we have, like we sample all this t uniformly, and we have this loss. That would mean that these samples here would basically get a weight of 0, and that's kind of useless. And that would mean we took some time to take a step in a direction that basically was useless because the gradient will be basically 0 since the weight is so low. So instead of doing that, where you're sampling uniformly and you have this, it's basically a waste of time because you're downscaling the loss for some of these time steps. You can alternatively sample differently. You can sample your time step differently. So instead of sampling uniformly and weighing your loss, you can instead sample with respect to a distribution that looks similar to this. So let's see what they say over here. Let me go back up. So if we look here, they say, in practice, we sample the random variable u from a normal distribution here and map it through the standard logistic function. So I'll show that, but basically that says instead of weighing everything, and instead of sampling your time step uniformly and weighing the loss, you can instead just sample your time step differently. And that makes sense because I'll show you the function, but it's basically just it's what I showed below, where there's more importance to a value of 0.5 than a value of the tails. So yeah, that's the loss we're going to be modeling. Just here. So yeah, let's go to that. There is one thing I need to show before, and that is this how we load the data. So let me show that. If I go to this helpers function, so I mentioned before, it's really annoying to sample this data. I'm going to go back to show you how I do that. But basically, we have our data set here. So we have our image data set. And what we're going to do is we're going to sample a bucket. So this bucket will be, say, of size 128 by 128 or something like that. Let's say I'm just going to let's say we're doing this for, say, 256 images. This will give us a batch of a bunch of images of size 128 by 128. So this will give us a batch of it. I don't know how large that is. 64. Maybe if we're stability AI, this will be 12,000 or something like that. I don't know. But what we had to do is we had to send this through 4 different things. We had to send this through the VAE, We had to send this through the clip model. In my case, I'm using MetaClip. We had to send this through, in my case, this is going to be Gemma and ModernBird. It's also going to be some text, so a batch of text. So a batch of text where each part of the text corresponds to part of the image. So we had to send this through the VAE. We had to send this through Clip, Gemma, and ModernBird. And for a normal transformer, you basically sample some text, you throw it through your tokenizer, and you get your output tokens. This is easy. You can do this in less than a second. This is super quick. This is slow. So if you look at the stable diffusion paper, they say they do this all beforehand. And that is a problem because this requires a massive amount of compute to compute all of this beforehand. But not only that, it requires a ton of memory because if you have to compute these embeddings and just store them, that is, I don't have that much memory. So there's also a third problem. So the third problem is you can't change these embeddings once they're computed. So instead, what I did is instead of pre-computing all these embeddings, I compute them on the fly. So I have 8 GPUs, and that's supposed to be an 8. So I have 8 GPUs that I wanted to work with. What I did is I designated some GPUs to load in the data while the other GPUs are running the model. And there exists a balance between these such that the time it takes for one model to load to process a batch of data, it should be able to process this batch of data as another model does a forward pass. So I'll draw this out for, say, so I use a batch size of I forget, I changed the batch size, but I use a GPU. I have some A100s. Well, I don't. My school provides it. I have access to A100s, and so I have 8 GPUs total. I use one data GPU to 3 model GPUs. So basically, I have so I have a data GPU, and I have 3 model GPUs here, here, and here. What this does, this data GPU, is so I don't know what my batch size is, but it takes 3 times the batch size. It then samples some part of this data set, and it processes all that data. So this data GPU, let me move it down. So this data GPU, it takes the data from the data set. So this is our image and text data set. It'll sample from it. It gets this 3 times B batch size because we're going to be using this for 3 different models. So it takes us 3 times B batch size, and it will process this through the VE, the clip, Gemma, and ModernBird. And it will produce these outputs. This will be the lane representation of the image here, or for all images here, of size 3B. It'll produce all these vector outputs of size 3B, and it'll produce all these big tensor text outputs of size 3B again. And while this is happening, these 3 model GPUs will take the previous batch that the data GPU processed, and it should do a forward and backward pass on them. So this will do a forward pass and a backward pass using set data. So once these models are done, and once this data GPU is done, which hopefully should be around the same amount of time, this data GPU will send the batches of data to the models. So it'll take this and it'll send it to all the models. So it'll take the first part of each of these here. It'll send it to model 1. It'll take the second part, send it to model 2, and the third part, send it through model 3. The models then take all of these and then do a forward pass. So forward pass, and then a backward pass. And while this is happening, after the data GPU sends this batch of data to each of these models, which are on 3 different GPUs, the data GPU is then processing the next batch. So basically, this data GPU is processing the next batch of data as these other GPUs are processing are doing the forward and backward pass. And this way, you don't have this latency with processing all the data. Because if you did, it takes forever and it's way too slow and you wouldn't be able to train anything. But also it allows me to uh, not have to need hundreds of terabytes of storage to store all these embeddings, but I can also edit these, since these aren't pre-computed embeddings, I can change these models. For example, I changed to T5 later. I wouldn't be able to do that if I pre-processed all the embeddings because I probably wouldn't have enough time to change from T5 to say modern BERT or Gemma, or the computer do that. But since it's computing on the fly, it's fine. The downside is I have two less GPUs. I said I'm working with 8, and I have 3-to-1 ratio. That means I have two GPUs that are solely working on the data. But price you pay for not having to process everything. So yeah, that's how I do this. Now let me show you how I code this. So like I said, I initially used T5 and clip, but I changed to not do that. Uh, So I'll just go through that. That's why I called it Vey T5 and clip. But basically, I'm using Flux as my Vey. I think I initially used the Stable Diffusion one, but Flux is better. So why not use it? And it takes about the same amount of time. So Flux, this is just a downsample factor of 8. And I removed the decoder because you don't need the decoder here. So I also freeze all the parameters here so that I'm not training it, and I put it in eval mode. One thing is I tried to compile these models, and it actually was slower. So I don't know, torch compile sucks, I guess. So that's the Vey. And I have this forward pass function here. Basically, it's a normal Vey forward pass. You encode the data. You want to sample your latent distribution. So you want to sample it instead of taking like you could take just the mean and standard deviation, but then you don't get any variance, and the model won't be able to learn the entire distribution. It only learns these discrete points. But if you sample it, it should be able to learn the entire data distribution. And then this is a scale and shift factor. So if I have a Vey, it'll output hopefully a mean of 0 and a variance of 1. In reality, it won't do that. So there's basically you can compute the mean and standard deviation that it typically produces and shift the distribution in that way. You want a mean of 0 and standard deviation of 1 so that you can model this well. Models work well when there's a mean of 0 and standard deviation of 1 because of precision issues. So this kind of just fixes that. Scales it down, like you can send a batch of data through, see what it gives you, and just scale it down by that much. I forget what these values are, but they're there. Clip. So in my case, I use MetaClip, which is much better than clip made from 4 years ago or however long it was ago. So MetaClip here, I use the 400 million version, but there's also a 2.5 billion. I just use 400 million. So yeah, MetaClip, and this is going to be used to give me the vector embedding. I just wanted, since I'm using Gemma and I'm using Modern BERT, those don't give me vector embeddings, but I need a vector embedding to manage or to control the statistics of the model. This gives me that. So clip processor, clip model, uh, remove no gradient, so it doesn't update the model at all. Put it in eval and half precision. So don't train it, half precision. And I think it's just an output projection. So here, basically, processor, so it's just a Hugging Face thing that processes the data. I think it just encodes it, adds padding, truncation. Basically, you want it to be all the same size. I forget how large it is, but it's just giving you a vector embedding, so whatever. And then send it to the right device. So this is just pre-processing, just encode your text, and this is getting the vector output, and this is, I think, this is just the text projection on your output. So it's just normal clip. Just clip vector embedding. Here, this is Gemma 2B. What this does is it just loads in Gemma 2B. It puts it in eval mode, and it is in half precision, vflow 16. So specifically, you want this to have a padding size of 77. Yeah, max length of 77. So every you want it to have a set token size. So this is a max length of 77. Uh, that was what Stable Diffusion 3 used, so I'm using the same thing. And this will truncate the text to have a max length of 77, but I also pad it to that much. So that means the output may have padding tokens in it, but that's fine. The model can learn how to deal with that. Um, it's not a big deal. So this is just tokenizing the text. This is sending the tokenized text through Gemma, gets the last hidden state, which is just the outputs of Gemma directly, and this here is masking the output. So in your output, Gemma, like whenever you're doing transformers, the masked tokens are masked in attention, but you don't care, like if it goes through a feed forward layer, you just process that and you just process that like normal. So these will still go through feed forward layers because the feed forward layers, it doesn't matter if it goes through that. But that means the outputs will be this weird value. So I mask it to be a value of 0 here. Just so the model learns, oh, there's a 0 here. It's useless information. Like you could probably learn that anyway, but I forcefully make it 0 so it doesn't have to. And then here, this is Modern BERT. Modern BERT is fast. It was made to be fast, so I'm using that. So this is loading in Modern BERT, setting it in eval mode, so don't train it. And yeah, this is just generating some text, or this is just generating the outputs. So hit again, max length at 77, send the text through, get the last hidden state, and mask it here. So yeah, that's loading in all the data. Now for the fun part. So this here is, yeah, this is just converting the images between 0 and 1, or between -1 and 1. So this here VE T5 clip is only going to be run on the data GPU, or yeah, on the data loader GPU. The model GPUs will not be looking at this. So this data, so I'll show you where this is happening in the trainer, but just know all this code is only happening on the data GPU. So you'll see it is sending information to a model GPU in a second, but I haven't shown where it's picking up that data from yet. Is this the most efficient way? Maybe not, probably not, but it works. So yeah, this is loading in the data set, and this is just loading in the data. So I have all the data in, it takes a while to encode it into bytes, to encode images into bytes. Well, I say it takes a while. It doesn't take a while. It takes, but it's really fast to read it back from bytes to an image. So I store it as byte information so that it's smaller, and it's easy. You can actually store in a Parquet file. I don't know if you can store images in Parquets, and it's just transforming this by doing like it's just converting this between -1 and 1, no transformers at all, and yeah, it's just loading in images. So here I do a 50% chance of doing a short caption and 50% chance of doing a long caption as it's loading in the data, but it's basically just a data loader right here. So yeah, again, data loader, it's loading in that data set that I have that is bucketed already. So it has this bucketed data set. So if we go to this bucket sampler, which is something, it's a custom data set I have, a custom data loader. This loads in all the buckets here. So this is done beforehand, before the model is, before everything is happening. So beforehand, this data GPU basically indexes all the buckets. So it says, here's my data set. I'm going to create a dictionary where the dictionary has the keys as, I think it's here, bucket dict, here. Yeah, so it has the keys as the bucket, so that would be size of like 16 by 128. And the values are going to be the indices of the images of the bucket. This is an inefficient way of doing it. Uh, it works if you pre-process all the indices. There's definitely a better way to do it, but yeah, I basically pre-process all the indices and throw it in this dictionary. And the reason I do that is that you can sample this. So the data loader now knows every single bucket. It knows exactly what indices are in every bucket, and it can easily sample from there. So what the data loader does is it just loads that in, and it takes in this list where the keys are the bucket the bucket sizes, and the keys are again the indices, bucket size and indices, and it creates this order, and it creates this ordering, and it creates these probabilities, and the probabilities are according to the size of each bucket. So I talked about this earlier, and basically the way I was thinking about this is if I have a bunch of buckets, and there's going to be some buckets that are garbage, like 16 by 16, and some buckets that are good. And if the data is representative of the data people want to generate, then the model should learn that as should be trained in the same way. So I don't want to train the model on 16 by 16 images as much as I train it on 256 by 256 images. So this is basically sampling buckets according to their frequency. So that's that there. And I think I also remove yeah, here I remove small buckets. So if buckets are too small, I remove them from the data set. Yeah, so that is this here, creating the probabilities. So this is just pre-processing everything. Now, whenever the model is actually doing this data loading process, whenever, or not the model, whenever the data GPU is actually doing this data loading, it's going to do it infinitely. And it basically just it samples a random bucket here. So samples a random bucket, and it gets a random set of indices from that random bucket. And that's it. It just returns those indices, and it loads in all that data. So this just returns the indices of the data, and the data loader actually loads in that data. And the way it does that is up here by just taking every image, loading it in, and just giving the image in the text. So you can see here the output it gives is the stacked set of images, and we can stack them because they're all the same size, and just a bunch of text captions here. So now that the data loader is created, there it creates a process for each GPU. So basically, well, actually, I don't think I use this anymore. Yeah, I don't use this anymore. What I initially had is I had these processes that would I had three processes or I had a process for every model GPU, and these processes would be sitting waiting for the main thread to send data to them, and they would send the data over to the model. But that took a while, so now it's just a direct process where the main thread sends it to every model GPU, and that worked way faster. So this here is actually not used anymore. I don't think. So yeah. Anyways, this data GPU is going to then iterate over the data loader forever, and it'll sample. So I showed over here how it's doing all the how it's iterating over this data set, but basically samples this. It samples a bucket. It gets a random set of data from that bucket, and it is sent here. So it takes in the images and the text, and it does all the encoding here. So it sends it through Gemma, sends it through ModernBERT. It concatenates the two embeddings along with zeros. So ModernBERT has a dimension of 1024. Gemma has a dimension of 2304. So I add zeros, which is what they did in the Stable Diffusion 3 papers, so that the embedding dimensions match. And then you concatenate them along the sequence dimension, so that this is of size 77 by 2 by 2304 here. So that is that there. Just encode using Gemma, encode using ModernBERT, add some padding to the ModernBERT outputs to make them of size 2304, and concatenate them together to give you your hidden output. This is throwing it through the VE, so that does exactly what you would think does through the VE. I don't think this is needed anymore, but it is there. I don't know why. It's not. It shouldn't be needed anymore. But basically, it sends it through the VE, and yeah, that gives you your output. And this sends it through the metaclip model here, the text. So yeah, I mean, pretty basic. Just sends it through the three models, and it batches them. So again, For me, I'm using one data GPU to three model GPUs. So what this does is it takes in a batch size of 3 times whatever batch size the models are going to be processing, and it processes that as a single batch, and then it splits it into 3 different batches so that it'll send to the model. Now here is where it actually sends it to the model. So it does this pipe.send. So if I go to, where's pipe? Pipes here. So pipes are going to be these connections that the model and the data GPU will communicate with. So those are here. Yeah, basically it's just these pipes that will be communicated, or where the model and the data can communicate with each other. And basically, this will sit here waiting to send information to the model GPU until the model GPU is ready. And I will show you that once I get to the trainer in a second. But basically, this will send it to all 3 GPUs. And I found it was faster to just iterate over that and send it. But I mean, I'm not a network engineer, so there's probably a better way to do this. But basically, it just sends all the information to each of those model GPUs here, and it sends it one at a time. Like I showed up here, I split it into 3 different batches, so iterate over all 3 batches and send it one at a time. This is the fastest way that I found to do it. There's a better way to do it. There definitely is. And I haven't thought about it much, but it worked. So yeah, this is the data GPU. This is what the data GPU is going to be running, this thing right here. Basically, just a data loader that's loading in data and sending it to the models as it needs it. Now we can get to the model trainer. So the model trainer is this thing here, which is very large, but it's not that special. But basically, there's going to be 8 GPUs that I'm running, and if the model, so I basically index, so if I go to train, I have these set of indices here. The ones that matter are these first two, and basically if the GPU is index 0 or 1, it'll be a data GPU, and this is what GPUs it's mapped to. So data GPU 0 will be mapped to model GPU 2, 3, and 4, and data GPU 1 will be mapped to models 5, 6, and 7. And it goes up to however many you want, hopefully. I think I tried this on 16, but that was a while ago, so it may not work anymore. But basically, this is just managing the mappings here. This is just putting it on the GPU, and this is initializing DDP. So if we go to initialize distributed, basically this is just a bunch of boilerplate code that initializes it for DDP, so distributed data parallel, which allows me to process it, which allows me to have 6 GPUs that are processing data in parallel. So DDP, data parallel, distributed data parallel. So I can process a batch size that is 6 times larger, essentially. Yeah, again, just boilerplate code. This should work for more than 8 GPUs. I need to test that again. So yeah, just initializing DDP. So you only want to initialize this for the model GPUs. If you initialize this for the data GPUs, it doesn't make any sense because the data GPUs aren't working with the model. So the model doesn't need to be on those. It just needs to be on the model GPUs. So that is this here. It just loads in the model for the model GPUs. This here this here calls this here. So this this takes every data GPU, and all the data GPUs are stopping here. So the data GPUs will run this forever. The model GPUs will continue down. This barrier basically waits for all the model GPUs to finish their setup of DDP up here, and it allows it allows them to not wait on the data GPUs. The data GPUs will call this function, or will call this class here, and this class is just loading the data forever. So and sending it to the models. So that's this part here. Um, there we go. I don't know why it froze up for a second. It is freezing up for some reason. Wait, I think it's good. Yes. Okay. I'm running this on a mid laptop, so whatever. Yeah. So this is yeah. Back to it. That's that part here. Um, and this is just the model GPU knowing the index of the data GPU it needs to look at, which will be important later. And this here is an EMA model. So this EMA model is an exponentiated moving average of the actual trained model. So this model will be updated every 100 steps, and um, it'll be updated like this. So the weights of the EMA is going to be equal to 0.99 times the weights of the EMA. So what were the old weights of the EMA plus 0.01 times the current weights. So we have this model that is being trained, but it's moving very, very fast. It's being trained, it's being updated a lot. This model here basically smooths out that update. It is much more stable, and it usually is better. It usually produces better outputs than if you were to just have a normal model that didn't do that. So typically you see this in large models where you have this EMA model, which it's more resilient to noise, while this current model is a lot less resilient to noise. So if you have a bunch of weird batches, it could mess up your original your fast model that's being updated a lot. But having the CMA model helps with that. Yeah, so that's the EMA model, and I'm keeping that on the CPU because there's no reason to have that on the GPU. You'll see that updated later. I'm using Atom W, just normal Atom W. Learning rate scheduler. I am using a learning rate scheduler that looks like this. It's it has a warm up and then it has a linear decay, except I decided not to have a linear decay, so it just has a warm up. So basically no scheduler at all, but the scheduler exists if you want to use it. And then this is loading in a bunch of states. So like if I have a model that died on me, I can load it in easily. So I save the model every now and then, and this allows me to checkpoint the model. You have to checkpoint a lot of different things whenever you're using AMP, automatic mixed precision. So there's a lot of things here that I'm saving. For example, the EMA model, or the scheduler, or the scaler, which will be used for EMA later. I'm also using weights and biases here. So weights and biases. I am turning off the gradients for weights and biases because that takes up memory, but it's there. And then the time sampler. So remember how I said we can either we can either sample time uniformly and then weigh the loss differently, or we can sample the time step differently and weigh the loss uniformly, or weigh the loss normally. This here does that. You sample from a random distribution and throw it through a sigmoid, and that is the same as the way I showed earlier on how you can model or how you can weigh the loss. So that's the same thing here. This is uniform. This is you take a sample from a Gaussian and throw it through a sigmoid. And note that the sigmoid is a value between 0 and 1, so it makes sense that that would be a function you would use. So yeah, sigmoid, or take a Gaussian, throw it through a sigmoid. And intuitively, if you look at a Gaussian, so a Gaussian has values between negative infinity and infinity. If the mean of the Gaussian is 0 and the standard deviation is 1, then you have a large mass at 0. And if you map a value of 0 through a sigmoid, you get 0.5. So the mass is at 0.5, which is what we thought of earlier. And mathematically, it's the same as the function they had for weighing the loss. It's the same idea, and it's mathematically the same in expectation. This is just sampling the time step differently. Sampling here, where u is sampled from a standard normal and then mapped through a sigmoid function rather than just a uniform time step. So time sampler, which will be used later, and then this is just saying how many parameters there are. So this is just set up. This actually trains the model. Basically, they're called in sequence, so it doesn't really matter. But this puts the model in train. This is just a bunch of setup. If it's the main process, do weights and biases and wait for all the models. So this is just iterating over all the data, except remember this doesn't iterate over the data, this waits for the data GPUs. This is just iterating for some number of steps. The data GPUs are running forever. This is just iterating for some number of steps, which looks the data GPUs. So this part here is what actually gets the data from the data GPUs. So this, what you have to do is you have to create these empty tensors here. So we need to create empty tensors, and we need to know what size data is actually being sent. So, oh wait, I know why I had that there. So here we have three tensors that we're expecting. We're expecting batch x0 to be of shape batch size by however many channels there are from the VE in Stable Diffusion, in the normal Stable Diffusion one, whatever that original one was. I think it's 3 channels, while in the Flux one it is 16. And we expect to downsample by a factor of 8. Now, one thing is you can't really change the size, at least to the best of my knowledge, you can't change the size of these tensors because you have to know what data is being sent from the GPU. But if you already know what data is being sent from the data GPU, then you have to send a request, and that's 2 more requests you don't want to have to make. So what I do is I instead, that's why I have this here, I pad the output of the VE, and I make sure it fits the entire size. So if I have a max resolution of 256, the output could not be 256, but I pad it such that the max size is always 256. Therefore, the tensor, or not 256, 256 divided by 8. Therefore, this tensor is always going to be of the same size, which is going to be the max size that I'm modeling for whatever data this is. So there will be some padding in this output, and the padding is removed down here. I'll talk about that in a sec. The text is always the same size. It's batch size by 77 times 2 by 2304. So that's just the text, and the pool embedding is also the same size. Batch size by the class dimension. So these are pretty simple. Basically just creating the tensors, but they have to be the same size as the tensors being sent over here. If they're not, you will run into issues. So this is saying, give me send data. So this here is doing a pipe.send here for the image data, the text data, and the text pooled data. So pipe.send is a function that I have above, and it takes this dictionary here. If I go up here, I think it's right here. So it takes said information, and yeah, so I have this one thread here, or so I have these 3 threads here, and these 3 threads here are basically waiting. So I mentioned earlier I didn't do this. I'm realizing I actually did do this. So there's the main data GPU thread that is processing all the data, and then there's these 3 model threads that are sitting there waiting to send data to the model. Oh no, it's the main thread. Yeah, so basically what will happen is, yeah, I think pipe. Where's pipe? Right here. Pipes.append, parent connection. Yeah. So it creates these three pipe connections. Sorry, these 3 pipe connections that will send data to the model GPU. And it was an old version. Yeah, so these 3 pipe connections, and basically these pipe connections will take in this dictionary, this main thread processes, where each dictionary is going to be it'll have images and it'll have the text parts in it. So it'll take that and it'll wait for the GPU it'll wait for the model GPU to basically say, hey, I'm ready. So the model GPU will say, hey, I'm ready by doing this dist.receive, and this will do a dist.send. So this GPU here, this is a blocking call, and it'll wait for the model GPU to say, hey, I want some data. And the models, and whenever that model makes a request, this will send the image data. And then the next request the model makes, it says, hey, I need some data. It'll send the text, and the next one, it'll send the pooled data. And it knows what GPU this needs to know what GPU to ask. So it looks at the loader GPU and it says, hey, I need some data. And this sends it to GPU N for whatever, to all three GPUs it's mapped to. So the model GPU basically requests data for one GPU, while the data GPU sends all the data to these three GPUs. That's how I'm managing this here. So once it requests this data, these three tensors will be filled as opposed to empty, and this is removing all the padding here. So this removes the padding in batch x0 that I had before, so that I ensured the data was always the same size. That's just removing that. Oops. And this is sampling the time step. So once we have the batch of data, everything's easy. You sample the time steps. This is a random value between 0 and 1 according to this logistic normal distribution. These are the probabilities of masking Gemma, Bert, and the pooled vector. And again, it's a probability of like 0.3, I think. I always forget the value, 0.316, so that we're masking with a probability of 10%. We're masking everything with the probability of 10%. This here is noising the batch. So if I go to the model, I don't know why I have the function in here, but I do. We take here. This takes the time step and it takes the current batch of images and it just noises to said time step. So I actually sample a batch of time steps, so each image will be noised differently. But basically all this does is this here. So it samples some random noise for every image and it does 1 minus t times x plus t times epsilon. So that is the velocity. So this gives you the velocity and the noise, and we need the noise so that we know what loss to model. This here is masking with a oh no, this here is the text loss I was experimenting with. Again, reiterating on that, if the model or if the model isn't following the prompt that well, maybe if the model has to model the prompt by doing next token prediction, maybe it since it actually has to learn how to use this text, maybe it'll help it. It was just something I was playing around with, but this isn't in the final model. And this here is AMP, so this is saying use bflow16 with automatic mixed precision. This is sending all the data through the model. So I talked about the model earlier. This is just sending it through the model here, getting the velocity prediction here. And this here is the velocity, so epsilon minus x0. And this here is just MSE between the two. So yeah, that's what you would expect. This here, so again, we don't need to weigh the loss, but if you wanted to weigh the loss, you would use this mess here, which I think is right, assuming my parentheses are right. I got them wrong one time and the loss was off, and that sucked. But it's much easier to just sample a time step differently, and it's much more efficient. So this isn't used unless the loss is weighed instead of the time step. So once you have your velocity prediction, you have your loss, you then do backpropagation. So this is doing that. So for AMP, you have this loss scaler, and this loss scaler scales the loss so that if you're using floating point 16, the value if you have it may run into precision issues. So scaler fixes that by I think it makes the loss larger, and then it'll scale all the gradients down afterward. So that's what this thing does here. It does backprop, it scales the loss, does backprop, and then you'll unscale the loss later. This is just keeping track of the losses for logging purposes. This here unscales the loss here via the grad scaler. So we scaled the loss, we computed all the gradients, then we unscale it. And that's just so we don't run into precision issues. This here is clipping with a value of 1.0. So there are no weird gradient outliers that kill the model. This is stepping the optimizer, gradscaler.step. I don't think gradscaler.step is needed because I'm unscaling manually here, but it is there nonetheless. This is stepping the scheduler, and this is updating the gradscaler, and this is zeroing out the gradients in the model. And this is weights and biases. But yeah, I mean, overall, pretty simple. Every 100 steps, the EMA model needs to be updated. So here is what I showed above. If you, it's basically iterating over all the weights, and for every weight, it multiplies it by a value of 0.99, so it scales down it basically does 0.99. So what I showed before, the EMA model, the EMA weights are going to be equal to 0.99 times the current EMA weights plus 0.01 times the current model weights. So we have this fast model here, which is updating the EMA model every now and then. And then this is saving the model every now and then as well as it's saving the model as well as the optimizer and everything like that, so you can checkpoint. Now finally, I'll go over inference. So inference should be quick. It has a script here, which is slightly different, and I won't go through it. It's not important or useful, but the one thing I will go over is how the model actually samples. So if we have a trained model and we load this model, in, it looks like this. So we create some random noise, and this random noise will be created in the latent space. So notice here, like maybe I want an image of size 512 by 512. So I create this image of size 512 divided by 8 by 512 divided by 8 by however many channels there are. So we create some noise in the latent space here. And then I create these text embeddings. So these text embeddings are it's the exact same thing the data GPU is sending over, except I don't have a separate GPU to do that, so it's just the same exact script that does everything, except it takes this text and it gives you the embeddings. So this will give you the vector embedding and the big embedding that is in the dual stream. This here is this is the node class. So you need to double the size of your embedding so that you can do CFG. You basically have a null embedding and you have a not null embedding. So normal CFG. So this is just, so if I have my image here, so my image is going to be equal to my image concatenated with my image. And remember how before the model is taking in these masks. So the mask is going to be equal to 0 and 1, where I say, well, actually, I guess it would be text. So the text embedding would be equal to this. So it's just doubling the batch size of the text embedding. And the model will say this first text embedding I will treat as a normal text embedding, and the second one I will treat as a null embedding. So this is just a trick so that you don't do 2 forward passes, you do 1 forward pass with a batch size that's doubled, where the second half of the batch is just a repeat of the first, but without with the null embeddings. So here is iterating over your time steps, and basically we have a model. I have it described right here. So we have our model, which is predicting VT, epsilon minus XT, so it's predicting this here. So VT represents how X changes so VT is basically our velocity. And what we want to do is we want to move, so our velocity basically says what direction, so I'm currently at XT. What is the direction, what is the direction I need to go to get to X at time 1, my completely noised version of my image. Instead, we want to take a step in towards X0, so we take the negative of the velocity. So that's what you'll see down here, and basically we're just going to be stepping in the direction of the velocity or in the direction of the negative velocity over and over and over again. So this is iterating over how many time steps you want, so maybe you want to sample this, say, 100 times, and this is creating a bunch of time steps between 0 and 1 with that value. So it starts at value 1, and it iterates to value 0, and it'll decrease as we change this. So this is just repeating t, and this is getting our velocity prediction. So we send the images through the model, and we get 2 predictions. We get the velocity prediction for the null embedding and for the not null embedding. And this allows us to perform CFG with our velocity prediction. So we're directly doing CFG on the velocity. So CFG here is 1 plus the CFG of the null embeddings minus the CFG for the not null embeddings for the uh, class condition embeddings. So this gives you your velocity prediction. dt is going to be 1 over the number of steps, so I mean that's pretty simple. So if it's 100, this would be 1 over 100, which is our step size because we're taking uniform step sizes. So here, this is stepping in the direction away from exit time 1, so the direction towards the image. And yeah, this is just normal Euler sampling. I have some other samplers here I was playing around with, just to try it out, but it wasn't that effective. And then at the end, it decodes it using the VE. So basically, we take a bunch of steps. We take a bunch of steps here. It iteratively computes the velocity, steps away from the or steps in the negative direction, computes the velocity, steps in the negative direction, and you do this over and over again until you get to time step 0. And at time step 0, you'll hopefully have an image which you can then decode here. And yeah, that gives you your output. So that is this here. So yeah, that is hopefully everything that is important in here. But yeah, these are the images it can produce, which I don't know, I think they're fine. Um, hopefully this was helpful in some way. I mean, if you have any questions, let me know. This is yeah, I mean, let me know if there's any problems if you try to use the code either. But yeah, Stable Diffusion 3, it mostly coded. There are a few things I didn't code. For example, as you change the resolution, so I did code as you change the resolution, it does change how you want to scale your rope theta, but you also need to change a few extra things which I didn't code, so the resolution scaling could be fixed a little bit. But besides that, it's almost it's pretty I think it's almost up to the paper. You just need to scale this to however many GPUs they used, and hopefully you get Stable Diffusion 3 quality. Probably not, but yeah, I thought it would be interesting to just go through it and code it and yeah, try to make a repo that people can use. But yeah, let me know your thoughts, I suppose, if there are any problems with it, if it actually does produce outputs that look like this. Um, yeah, there should be everything here. But yeah, hopefully that's helpful.